3.3 Characteristics of polynomial functions in factored form. Okay, behavior of a polynomial at the x-intercept, zeros, or roots. Okay, so just a little bit of a review of wording. If a question asks for the x-intercepts or zeros or roots, those all mean the same thing. It could also ask for like, what are the solutions? Okay, the multiplicity or order, I'm actually going to refer to it as order. So the order of a root refers to the exponent of each factor. So if we can recall, a polynomial written in factored form contains a root in each of its brackets. Okay, so if f has a real zero of odd multiplicity, so if it's if the order is odd, that's what we'd call it. If the order is odd, then the graph will cross the x-axis. Okay, and then if the function has a real zero of even multiplicity, so if the order is even, the graph of f will touch but not cross the x-axis. Okay, let's take a look at what this actually looks like when we're drawing graphs. So up until now, we've only really focused on single roots. So multiplicity 1 or order of 1. So this is when the curve crosses the x-axis at a point. So we have a cubic function here, and we have x minus 1, so it goes through at 1, x plus 2, it goes through at negative 2, x minus 3, it goes through at 3, okay, and there's 3 roots there. All of these factors have an exponent 1 on them. That means it goes through. Now, we have seen this one before, the double root or a multiplicity 2, order of 2. Okay, the curve touches the x-axis at a point but does not cross it. So, like x minus 3 squared. So this here shows us that it's order 2, and this is just a parabola, but we know that the vertex of this parabola lies right on the x-axis, and then it returns. Like, for example, these are all positive y values. It returns to the positive side. Okay, this is a local max or min at this point, because we can know that this is a turnaround point. Okay, and then triple root. So we've only really seen this in the y equals x cubed, like that base function with no transformations. Okay, so what that looks like, so order 3, what happens is the curve crosses the x-axis, but it actually like wiggles. So it's no longer like a smooth curve where it just crosses the x-axis. Okay, there's a wiggle in it. Okay, or a point of inflection. Okay, so we've talked about points of inflection. We'll get more into that in calculus. The curve is concave up on one side and concave down on the other. So we have this function and it like flattens out here. And just for this split second right in the middle of like that wiggle, there will be a horizontal tangent line where the slope is 0. Okay, so this is a turnaround point. It's neither a max nor a min. This is actually like a point of inflection. Okay, and if you think about like if we kind of continued this like this would be concave down, and if we kind of continued this one, this would be like concave up. Okay, so on one side is going to be concave down, the other side is going to be concave up. So example 1, for f at x equals x plus 2 cubed, x minus 1 squared, label the zeros on the graph, and provide and describe the behavior of the roots. Okay, so the zeros would be negative 2 and 1. Okay, another way of doing that is if we have f at x equals x plus 2 cubed, x minus 1 squared. Well, it's really easy to come over to the graph and just label them. However, what we're actually doing when we're finding the x-intercepts is we're saying, when does y equal 0? So if you're thinking of these, like the height being the y, this number here is 0. So when's y 0? Okay, so we would sub in f at x like 0 to this entire side, right? That would be y or f at x. And then x plus 2 cubed, x minus 1 squared. So what happens here is we have two situations. We can either, if this factor equals 0, then this entire side equals 0. And if this factor equals 0, then this entire side equals 0. So there's two situations here. So we're thinking to ourselves, when does x plus 2 equal 0? And then we can just bring that over when x equals negative 2. Well, there's our 1 x-intercept. This is just algebraically. Now, when does x minus 1 equal 0? Well, bring that over when x equals 1. Okay, we saw this a while ago with quadratics, but it's back. Okay, so x equals negative 2. So both algebraic and graphically. So we see that x plus 2 has an order 3 on it. We can also see that this kind of flattens out that wiggle. So we can say order 3 goes through the x-axis. Let's just say with a wiggle. Okay, then we have x equals 1 right here. This one touches the x-axis and goes back up. Okay, so it kind of looks like a parabola if you think about it. And we can see that this is order 2 algebraically. So order 2 touches x-axis and returns to, let's just say, positive y values. Right? They're all positive y values. Okay, sketching polynomials. So first what we want to do is we want to plot the zeros. And we want to check the multiplicity of the root to determine which direction the curve will follow. Right? So the three options, order 1, order 2, or order 3. That's what we will cover in this course. Then we want to plot the y-intercept. That's convenient. And then what we can do is identify the end behavior of the graph accordingly. So we would want to see what the degree is and what the leading coefficient is, right? Degree, even or odd. Leading coefficient, positive or negative. And then go from there. Okay, so just a diagram here. So single root, say for example, x plus 3, that crosses the x-axis. I'm going to do roots first. Double root, say x plus 1 squared, it just touches the x-axis. And a triple root, which is like x minus 3 cubed, as an example, it forms an inflection point there where the curvature changes sign. Okay, sign means going from positive y values to negative y values. Okay, there are local maximums and turning points. Okay, and then there's global maximums and turning points as well as minimums. The y-intercept is when x equals, to find the y-intercept, we want to find when x equals 0. At that point, I'm going to say x equals 0. Okay, and then end behavior at large x. So end behavior at large x and small x. Large meaning infinity, small being negative infinity. Okay, so just kind of talking about a graph just in general, but it's going to make way more sense when we actually start to graph these. So let's go ahead and sketch the following polynomial functions, or polynomials. And just to take note here, polynomial functions always have smooth graphs with no discontinuities. And that's why our domain is always XER, no matter what. Okay, so let's reference up here. First, we're going to plot the zeros, y-intercept, and behavior. Okay, so zeros first. This is y equals 3, x plus 3, x minus 1 squared. So I want to speak to this 3. It has no x on it, therefore there's no 0 associated with it. Let's solve for x plus 3 equals 0. So there's going to be a root of x equals -3, and this is going to be order 1. So let's go here. We'll call this -3. Order 1 means it's going to go through. Okay. I don't want to draw this too quickly because I don't know if it goes up and I don't know if it goes down. So I don't want to lean those. Okay. And then we want to solve, when does x minus 1 equal 0? Well, of course, bring that over when x equals 1. And this is going to be order 2. So let's go ahead to 1 and we'll plot our x-intercept there as well. Now, y-intercept is going to be when x equals 0. So we go ahead and we sub in zeros, and we get 3 times 3 times -1 squared. -1 squared is just 1, so that can just cancel to 1, and we get 9. So we're going to have some point 9 that's going to be our y-intercept. Okay, now let's talk about end behaviors. So we have degree 3. If we were to take this and expand the whole thing, we have x to the degree 1 and x to the degree 2. That is going to expand to degree 3. Now, leading coefficient. Oh, I just want to note that that's odd. Okay, leading coefficient. Yes, we have x, and that would expand to x cubed. However, we do have a 3 in front of here, which will expand as well. So the leading coefficient is 3, which is positive. When we're thinking degree, like odd degree, we're thinking a line. Either it's going to go up to the right or down to the right. Now, if the quote-unquote slope is positive, we're going to go up to the right. So that will make our graph go up through 9. The 1, because it's degree 2, is going to be a max or min. So in this case, a minimum, and then up. Okay, the -3 was order 1, so we go through. The 1 was order 2, so we touch it and go up. And our end behavior is going to go from quadrant 3 to quadrant 1. Okay, B. So we have y equals -2x cubed, x plus 2, and this would be to the 1, and x minus 3 squared. So we have 3 different factors here, or 3 different, I want to call them x-intercepts. So because this leading coefficient actually has an x on it, we can say, when does -2x cubed equal 0? So if you want to actually do the work for this, we would divide both sides by -2. So then we'd say, when does x cubed equal 0? Well, the cube root of x cubed is just 0. So pretty much you can remember that if it's a monomial at the beginning, so if it's just one term with an x in it, the root is just 0. And we can go ahead and plot that. So when does x plus 2 equal 0? Well, when x equals -2. We'll plot that here. And then this one will be, when does x minus 3 equal 0? Well, of course, when x equals 3. Okay, so let's take a look at the degrees on these. For this x cubed, that would be degree 3. So this is order 3. This is going to make that wiggle. X plus 2 to the exponent 1, this is order 1. So it's going to just go through. And then x minus 3 squared, that's going to be order 2, of course. The order is just the degree. Okay, let's solve for the y-intercept. So for the y-intercept, do it over here. What we want to do is we want to plug in x equals 0. So here's the thing. If we have a root of 0, our y-intercept is going to be 0, 0. I already know that. Okay, so algebraically, y equals -2, 0 cubed, 0 plus 2, 0 minus 3. Here's the thing. If we sub in 0 cubed here, it's going to be 0 times something times something. It doesn't even matter what those two things are. In this case, they are 2 and -3. We're still going to get 0. So we're going to get the y-intercept of 0, 0, which we already knew from having an x-intercept of 0. Okay, and now the last thing is end behaviors. So the leading coefficient, just please note, if we had something other than just an x, like 1x in the bracket, we would have to consider if we were to like expand this entire thing. But in this case, the leading coefficient is -2, so it's negative. And the degree, I usually do first. We have a degree of 3, a degree of 1, and a degree of 2. If we were to expand all of these, we would have degree 6, which is even. So when I'm thinking even function, I'm thinking, or even degree function, I'm thinking that it's going to look like a parabola, leading coefficient's negative, so I'm thinking it's going to open down type of idea, right? So just a relationship to the parabola, and therefore we're going to go from Q3 to Q4. Okay, so Q3 to Q4. So let's start in Q3. And when we go through -2, it's order 1, so we just go through it. Okay, when we come back down and we go through 0, this is order 3, so we're going to wiggle. And then when we go back up to order, x-intercept of 3, it's order 2, which makes sense because we have to come back down. So this one doesn't look very good, but this is how we draw it. And that's it.